Hello students, today we will start contour integration. In this topic, we will discuss about some important integrals which contain straight lines and circular arcs. These integrals are evaluated by using Cauchy's residue theorem. The value of integral is equal to 2 pi iota times of the sum of the residues at poles within the contour C. So let's start. So now we see integration around the unit circle. Unit circle means a circle with radius 1 and center at the origin. Okay. So an integral of the type integration from 0 to 2 pi f of sin theta cos theta d theta can be evaluated by writing e to the power iota theta is equal to z. We put sin theta is equal to 1 by 2 iota z minus 1 by z, and cos theta is equal to half of z plus 1 by z. Then the integral from 0 to 2 pi f sin theta cos theta d theta will take the form integral around c f z dz. Okay? That means we are converting the function of theta and pi into the function of z. Okay? Now example, show that integral from 0 to 2 pi cos 2 theta d theta divided by 1 minus 2a cos theta plus a square is equal to 2 pi a square divided by 1 minus a square, where a square is less than 1. Right? Now we see solution of this problem. So we put e to the power iota theta is equal to z. Then we differentiate this function, then we'll get iota e to the power iota theta d theta is equal to dz. And this e to the power iota theta is actually z. So iota z d theta is equal to dz, or we can write d theta is equal to dz divided by iota z. Now again we take cos theta. So cos theta is equal to 1 by 2 z plus 1 by z. And z is equal to e to the power iota theta. So 1 by 2 e to the power iota theta plus e to the power minus iota theta. Right? And again cos 2 theta will be, we just replace theta by 2 theta here. Okay. So cos 2 theta will be 1 by 2 e to the power twice of iota theta plus e to the power minus twice of iota. Right. Again we replace e to the power iota theta by z. So the value of cos 2 theta will be 1 by 2 z square plus 1 by z square. Now we put all these values of d theta, cos theta and cos 2 theta in our given integral. Okay. So our function will become dz. This given function will become cos 2 theta is equal to 1 by 2 z square plus 1 by z square. Okay. Now 1 minus 2a cos theta plus a square. So 1 minus 2a, again the value of cos theta is 1 by 2 z plus 1 by z, and plus a square. The value of d theta is dz divided by iota z. So it will be a given function. Now we simplify this function by taking LCM. Okay. So we'll get 1 by 2 iota integral along C z to the power 4 plus 1 dz divided by here 2 and 2 will cancel each other. So, and we take z as LCM. So, we'll get denominator as z square into z minus a z square minus a plus a square z. It is very simple calculation. You can do it on your own, right? So now we factorize this term, okay, this denominator. So we get 1 by 2 iota integral along C z to the power 4 plus 1 dz divided by z square. Now we can take z common from these two terms and a common from these two terms. So after factorization we will get z minus a and 1 minus a z, right? So we are getting poles of this function at z is equal to 0, z is equal to a and z is equal to 1 by a. Okay. So we are getting poles at z is equal to a and 1 by a. Here we are getting simple pole of order 1. And at z is equal to 0. Okay. Here we are getting double pole. That means the pole of order 2 or second order, right? And out of these three poles, only z is equal to a and z is equal to 0 will lie inside the circle. Now z is equal to 0 and z is equal to a. These two poles lie inside the circle. Okay. Why? Because it is given in the question that a square is less than 1 and our circle is unit circle. Okay. So radius will be 1, right? So we'll find out the residues of the given function at z is equal to a and z is equal to 0. Okay. So we are getting simple pole at z is equal to a. So first we find out the residue of the function at z is equal to a. Here we are getting simple pole. So residue will be limit z tends to a, z minus a into f of z. So limit z tends to a, z minus a, we put the value of function which is 1 by 2 iota into z to the power 4 plus 1 divided by z square, z minus a into 1 minus a z. So this z minus a and z minus a will cancel out each other and this 1 by 2 iota is actually a constant value. So we can take it outside the limit. Okay. So 1 by 2 iota limit z tends to a, z to the power 4 plus 1 divided by z square 1 minus a z. Now we apply the limit here. That means we put z is equal to a here. So the value will be 1 by 2 iota a to the power 4 plus 1 divided by a square into 1 minus a square. Okay. So this is a to the power 4 plus 1 divided by 2 iota a square 1 minus a square. Okay. So this is actually the residue of the given function at the pole z is equal to a. Okay. Now we find out the residue at 0. Okay. To understand more about the poles and the residues, you can watch my videos based on these topics. Okay. So we find out residue at 0. Here we are getting double pole, that means pole of second order. So the residue will be limit z tends to 0 d by dz of z square into f of z. Okay. So limit z tends to 0 d by dz z square. Now I put the value of function 1 by 2 iota into z to the power 4 plus 1 divided by z square into z minus a into 1 minus a. Okay, so z square and this z square will cancel out each other, and 1 by 2 iota can be taken outside the limit because it is a constant value. So 1 by 2 iota limit z tends to 0 d by dz of z to the power 4 plus 1 divided by this value. We open these brackets. Okay. So and multiply these terms, then we'll get z minus az square minus a plus a square z. So again 1 by 2 iota limit z tends to 0. Now we differentiate these terms, then we'll get z minus a z square minus a plus a square z into 4z cube minus z to the power 4 plus 1 into 1 minus twice of a z plus a square and divided by z minus a z square minus a plus a square z and square of this term. Okay. Now we apply the limit z tends to 0. That means we put z is equal to 0 here. Then we'll get 1 by 2 iota minus 1 plus a square divided by a square. Okay. So it is equal to minus of 1 plus a square divided by 2 iota a square. Okay. So this is the residue of the function at z is equal to 0. Now we find the value of the function. Okay. So we apply residue theorem here. So value of function will be 2 pi iota times of sums of residues of the function at the poles which are inside the given contour. Okay. So 2 pi iota into residue of function at a plus residue of function at 0. Okay. By using residue theorem. By using residue theorem. Okay. So 2 pi iota, I put the values here. So a to the power 4 plus 1 divided by 2 iota a square 1 minus a square minus 1 plus a square divided by 2 iota a square. Now this 2 iota a square is common in both. So 2 pi iota divided by 2 iota a square into a to the power 4 plus 1 divided by 1 minus a square minus 1 plus a square. They will cancel out each other, and after solving this, we'll get the value 2 pi a square divided by 1 minus a square, okay, which is the value of function, right? So it is proved now